Good afternoon, everybody. Welcome to this KIOS Distinguished Lecture, which is going to be given by Professor Cesare Alippi. And Cesare is a professor at the Politecnico di Milano in Italy, and also a professor in the Università della Svizzera, italiana in Switzerland, which is, so it's, the big professors in Italy have two positions, so he's no different. Cesare is, I have known him for many years. He's one of the leaders in the area of, one of the world leaders in the area of machine learning, and also in the area of embedded systems, and especially intelligent embedded systems. So he has done a lot of work there. He's an IEEE fellow. He has won many awards, including the IEEE Computational and Intelligence Society Outstanding Computational Intelligence Magazine Award. He has won outstanding paper award for the transactions on neural networks and learning systems. He has also won the IBM Faculty Award, and also the Young Engineer Award from the IEEE Instrumentation and Measurement Society. He's in the board of the IEEE Computational and Intelligence Society, and in the Board of Governors, and also in the Board of Governors of the International Neural Network Society and the European Neural Network Society. He has done a lot of work, as I mentioned earlier. Today, he's going to talk to us about some of his latest work related to adversarial learning and learning in graphs. So this is a very interesting topic, and I think it's related to some of the things that we are doing at the KIOS Center of Excellence. And we are very, very pleased to have him give this distinguished lecture. So this, as you know, maybe for the people that are new to the center, we have established this KIOS Distinguished Lecture Series, where the objective is to bring some of the world leaders from around the world to talk about their research and to interact with the researchers at KIOS. So this is a great example for this, and I hope you will enjoy the lecture. So, Cesare.
Thank you, Marius. Thank you to everybody to be here today. It is always a pleasure for me to come to Cyprus, and it is always an honor to have the opportunity to give a presentation here. So that's what I'm going to do today. So the focus of my talk is on graphs. So why do we need graphs? That is the first point we needed to address, but as Professor Politecnico said, if we have cyber physical systems, if we have networks of sensors, graphs somehow come naturally. One of the major assumptions that people do assume once they design a machine learning framework to process the data coming from the field is that the data, or the structure that is representing the data, is IIDs. The data are following some independent and identically distributed distribution, which is not the case in many situations. And for sure, it is not the case where the environment is time variant. So it changes its behavior over time, which does not mean that we don't accept a dynamic. There is a dynamic, and on top of that, there is time variance. And in addition, I know that is what many of you are studying here at the KIOS. You might have problems in the interaction between the physical system, the sensor, the transducer, most of the times, and the environment, which means that the environment is not changing, is not drifting, there is no time variance, but the interaction between the readout system of your sensor and the environment provides data that are not coherent with the environment. You say that there are faults, anomalies, events. And that is exactly what we want to understand. So, we will enter into the framework of detecting changes in stationarity in graphs. And then we will see that in order to do that, it is a positive effect if we transform graphs from the graph space into some embedded vectorial space, Riemannian manifolds. Where there we can build some statistics and we can look at the probability that the data coming from the field are coherent with the stationarity hypothesis or not. If this stationarity hypothesis does not hold anymore, within a lifelong framework, we need our system to react to the change by modifying, for instance, its behavior. Or we might be only interested in what's going on. So we say something happened, and it happened there in time. So that is what we are going to talk about today, and we will touch different points related to, let's say, vectorial embeddings, and then neural embeddings coming from deep learning, adversarial learning, and autoencoders. Now, let's move at first. Let me try to convince you that nowadays it's very relevant to try to represent data as graphs. Why? Because in many applications, graphs come naturally. If we want to design new drugs, we start from molecules. And if I look at the atoms, those are attributes associated with nodes. And then we have the bond. And associated with the bond, we have a valence, the valence. And that is another attribute. So this is a graph. Well, if we look at our brain, it is a graph by definition, where we have the different neurons that are interacting with each other. In some other applications, we have, like in social networks, we have a group of people that, well, sorry for the quality of the picture, but so we have a group of people that are somehow related. Think of Twitter, of Facebook, social networks more in general, where you have strong ties between you here in the middle and people that are very close to you. We exchange on WhatsApp messages, texts. Well, we can look at what the information you are conveying to other people, and those are attributes associated with the edge. And we have pictures, we have different, I don't know, these are surfing friends, these are New York friends. You have different areas. We might think of building a graph here where each of these people are related to each other because they do share some knowledge. And then you have a hierarchy, or you might have a hierarchy of graphs, which means that your information is hierarchical, like here, where you have some strong ties, some weak ties between people, some temporary ties. You met a friend, you change very few pictures, and then the game is over, you don't want to see him or her anymore. So, what do we do here? If we look at time as it passes, since we do exchange information, I can take a picture of that, and then I generate one graph. Then time passes, a new picture. A picture means that I have a time window where I collect the data coming from this social network, and then I generate a graph with the attributes at the node, vertices, and edges. One day, something will happen. So we have this stream of graphs. They might change in terms of a number of nodes, number of edges, because everything is volatile in a way. However, if nothing bad or positive is going to change, all these graphs are associated with a stationary state for my process. So everything is doing well. Now we have some major problem here, which means that the community, due to some unknown, possibly external event, it is changing its behavior. Something happened, we don't know that, but the information that is moving through people has a different content, different information. And that is an example of changing stationarity. This is another example. Smart city, I did that for Professor Politecnico because I need to convince him at first that this graph processing is a really useful tool. So we have, this is an example, a smart city, different blocks. I'm interested in the power consumption of people because I want to do some profiling of that and then build some predictor over time just to see which is the best framework for that. So for each block, let's say I take, I don't know, can we improve the quality of the pictures? Because they are very nice on my laptop and I would like them to see. Because here there are plots up and downs and they are very relevant. But anyway, if you can do that, that will be very nice. But assume now that here there, maybe that if we can switch on the lights, maybe it will improve a bit. But anyway, here we have a signal associated with a time window, which is characterizing the power load profile consumed within this block. And you do that, you partition your city in different blocks, and then you generate for each of those, you have different information associated with a time window W1, you generate one graph. Where associated with nodes, we will see what we have, and associated with edges, we will have different attributes. Another time window, you generate another graph. Another time window, you generate another graph, and so on. Let's see which type of information I might decide to associate to the graph. So, for instance, in this smart city application, we might consider as attributes associated with a node some information related to the power load. There might be some spectral coefficients or wavelength coefficients because you want to represent the average power consumption over the time frame in a very compact way. You have, for instance, the external temperature, you have the date, time, the fact that it's a weekday, holidays, because that affects the power consumption, the number of inhabitants, so how many people do live in there, which is their education, which is the average wealth of those people. And you do that for each of these blocks. So one node has these attributes. You can add all the attributes you want. They can be numerical, they can be categorical. Between the nodes, we have dependencies. And the graphs are very advantageous. So they are the right structure if we have functional dependencies. For instance, signal correlation, Granger causality, Pearson coefficient between those numerical signals. And weather correlation. Nowadays we have no cast information. We have mountains, so here we have a shadow, here you don't have a shadow. You have a different behavior. So it's not the same. We cannot assume that. The cable length, which is a measure of the distance between those two blocks. You see, those are information that we can associate to edges. Therefore, over time, here again, you start from graphs. You have a time window, one graph, another time window, another graph, and so on, and you have a graph stream. Something might happen, and that is exactly what we want to detect. Or we have signals. These are 4 signals. Take one of those. I look at the signal, and from a signal, I can build a graph. The technique, one of those is the horizontal visibility graph. What does it mean? That if I'm here, I'm at a point of the signal, I look back at my up and down of the data, and if I can see them nicely, I'm on a hill, I see them below me, then there is a connection. If there is not, I don't build a connection. So by using this technique, if you look at the yellow line, you end up with this graph. if you look at the blue line, you end up with this, and so on. So starting from one signal, you generate a graph. Another example we have been working on is related to electroencephalogram, where the key point is to detect epileptic seizures. So in this case, you have several channels, 64 in our application. You have the readings. And what is interesting is that by looking at the signals, they are highly correlated or not highly correlated. We take a clip, a time window of the signal, we build a dependency graph, correlation between the readout coming from different channels. Pearson coefficient, that is an example. Pre-ictal, which means no epileptic crisis, epileptic crisis. If I take different recording and there is no epileptic crisis, and if I look at the graphs, they are different. They are different in nodes. They are different in the number of edges, and clearly they are different in attributes you have associated with that, because our internal activity changes. So what is very interesting is that once we look at these graphs, we cannot assume, as many people do these days, nowadays, that the topology is fixed, that edges are fixed. They are not. So, okay, so I hope that you understood why it is so relevant to talk about graph processing. And now I want to detect changes in those data streams, because something happened. So all graphs are equal, but some graphs are more equal than others. So those graphs are related to oval, and they are associated with a change in stationarity. Here, I'm not looking for single event. I'm looking for structural changes, which might last for a short time. Professor Politecnico would like to call them transient faults, for instance. Or can I use that to detect anomalous events? Yes. But the probability, the confidence I can build on the top of that is different. If I want to make a claim that something happened and that something is a structural change in my environment, I need to grab data from the field over time and build enough confidence that allows me to claim that something happened. The change in stationarity framework, just to give you the flavor for those of you who are not expert in this field, is very simple. Let's imagine that we have a scalar stochastic process P that generates a numeric sequence. It is a random variable. It is xt, and xt, so this random variable follows distribution f0, which is a known, up to time tau. These are realizations of that random variable. And after time tau, which is unknown, we have a different distribution. So we have a shift from one distribution to another distribution. We call tau the change point, and we would like to detect it. So yes, that is the point where my process generating the data changes its distribution. How can I solve this problem? Well, we need to build a statistics, which is looking at features, which will have some probability distribution. And then, based on that, we build a confidence level, and you say, yes, there is a change, no, there is not a change. So T-student test, if you want to assess changes in the mean, the Cousin test, the Hotelling test for multivariate vectorial information, and so on. I'm not focusing on the change detection test. You take your favorite statistical test. So, mutatis mutandis, which means that, I don't know if that is an English word, but it is a Latin one. So I take inspiration from what I told you in terms of numerical time series, random variable. We can do that conceptually also with graphs. So we have graphs that are generating from some graph generating process whose distribution is unknown. These are the ones. And once upon a time, something will happen to them, and I want to detect that point. I don't know if you can see that, but these, for instance, are characters coming, alphabetic characters coming from an optical character recognition. So you have A. But if you look at the number of nodes, they are different because there is an error in there. Okay? And now there is character E. And here you see that sometimes the graph is different still. It is a realization of character E. Which is the state of the art on this graph processing? Well, detecting changes stationarity in graph stream is a very difficult problem, and there are very few results on that. One is from Renshaus and others, where they have a graph, they extract one feature, and then they look at the behavior of that feature. They build a statistical test on the top of that. Barnett and Ornella, that's very nice. They consider a fully connected correlation graph. So you have nodes, Pearson coefficient, that is the attributes associated with the edge. And they look for changes in those numerical attributes. Wilson and colleagues, they look at change detection by adding a change detection test or statistical test to any single feature. They are assuming that features are numerical features. That's it, basically. What do we want to do is to build something which is very relevant in terms of impact in the society in a way. The first step is that we need to characterize the concept of graph. The second step is that we want to map these graphs into an embedded space, a vectorial space, where we have the concept of a distance, metric distance. And once we have these vectors in this strange space, we can build a change detection test, which is looking at the changes in distribution associated with this vectorial set of features which are coming from the embedding, the transformation. By doing this framework, we need to understand at first which are the correct space for graphs. We want to consider graphs which have generic attributes, numeric attributes, categorical attributes. They can be anything. I like, I don't like. That is a binary, but I might have some fuzzy category on the top of that. Variable topology and order, still being within a stationary framework, one graph and the subsequent one might differ in terms of topology, number of edges, number of nodes, still being in the stationary framework. We might have the case where we have identified vertices. So we have two graphs. They are coming, for instance, from the EEG application. We have channels. We know channel 1 to channel 1, channel 2 to channel 2. So they are colored. I can map easily one to one, the other one to the other one. Or they can be non-identified. So we have two graphs, and I'm asking myself, are they related? Which is the affinity, which is the distance between those two. But I don't have this matching. So topology and attributes can change over time, we said. So the graph space that we consider is called the graph alignment space, which has been defined only in 2016 in terms of mathematical terms. And it relies on a distance, a metric distance that here I call a graph distance. The key point, because then I will use something simplified just to, for ease of understanding, is that if I have non-identified graphs, I fix, and I want to see how close they are, I have one graph and the other graph. I build a kernel, I look at the distance, the affinity, and then I cannot map this one to this one. So I have to explore all the possible partitions and then do the match, and then do the match, and do the match. And then you take as a kernel distance the one that minimizes the discrepancy. And once you have that partition, you can look at the distance between those two graphs. I'm somehow simplifying that framework only for reason of understanding, and we consider the concept of a graph edit distance. Maybe that some of you know that. What does it mean? That if I have two graphs and I want to look at the distance, okay? So no kernels for now. I just want to look at the distance. What I have to do is to try to start from one graph and list all the possible operations that starting from this graph will allow me to get to another graph. How do you do that? You remove a node, you add a node. You remove an edge, you add edges. You have difference in attributes. You have to look at that. So basically, you have a cost for each of the operations that allow you to move from one graph to the other graph. You do this operation, you assign some weights to this, some cost, and then you have, oops, sorry for that, and then you have something which is telling you how close those two graphs are. In reality, behind that, there is also some fuzzy approach. There are algorithms which allow you to match, to try to identify those vertices that in probability are closer, because you don't know if they are matching one-to-one. So there are techniques that allow you to estimate the best matching, and then you match and then you evaluate the distance. Once you have a distance, well, we can do something, hopefully. There are some theoretical guarantees, some theoretical results we have been working on. They are not comprehensive, they are not addressing all the possible scenarios, they are making some assumptions, but they just want to show that if we have a graph streams, and we should build a statistic on the graph stream. That is what I would like to do. That is what we should do. Because the changes are here, are not in the embedded space. Then you build an embedding map, a transformation, and then you have numeric streams. You have other statistics there. And the key point of these results is that the p-values in the numeric test are related to those of the graph stream and vice versa. What does that mean? That by looking here, if there is a change, there is improbability, also here. And if a change is here, with some probability, I will be able to detect that also here. Results are deterministic bounds, which depend on the distance and on the manifold that you are considering. We are assuming some B-Lipschitz assumption, which means that you have a function which is a B by univocal. So from here you go to here and you come back. But that's not the case. So we extended that to consider the Frechet approach, where once you go back, you don't have one graph. You have a set of equivalent graphs. And there is all a statistic according to Frechet, which is the one that we are using, and is very interesting. Or you can work in probability. So you claim that the p-values here are related in probability with the p-values to the other side. And it is much more general, which allows you to say that in probability, those are related even though the bounds you are able to design are not very strict. Okay, so what do we do now? Okay, apart from the theory, we have something which is very complex, can change over time. We want to map it into something which is a numeric. So we do an embedding. If I'm not able to see changes in the graph stream, because it is too difficult, hopefully I will be able to make an embedding looking at the vectorial information I have there, and I have new glasses. If I'm lucky, I will see changes. Which type of embeddings should we consider? There are plenty of embeddings. I'm just going to present a couple of families to you because they are very relevant from my point of view, from my perspective. The first ones that you're familiar with are based on the distance-based methods or the similarity representation, and the second ones are related to neural approaches. So you let the neural network to provide the right embedding. Let me go a bit into details. The first one is the similarity representation. We have a set of graphs, that is our training set. From the training set, you extract some prototypes, which are representative of this distribution. If you don't know anything, you sample randomly according to a uniform distribution, and you put them there. There are much cuter algorithms, as you can imagine. But just let's see the concept. Now, the embedding is very simple. You have a new graph, GI, and you build a vector which contains the distances between that graph and the set of prototypes. So I have this graph. I take a prototype of 1. I do a graph edited distance. I look at the distance. That is the first component. I have that graph. I take another prototype here. I do the distance. That's another component. You build a vector. There are beautiful properties in this embedding. So if we should look at that, this is an example of a manifold with a 2 graph representation here. The manifold is completely restructured. So here you don't see that it goes down and then it comes up. The point is that that embedding changes completely the structure of what you have. Another approach based on the similarity representation is the multidimensional scaling, where you have a set of graphs that you consider for training and a set of prototypes. Now, you do an embedding of the prototypes onto some Euclidean space or some space. So in the green, you have the mapping of this graph into this Euclidean space, embedded space, and in red are the points. If you have a new graph, you want the mapped point to keep somehow the interdistances with respect to the prototypes. So I'm a new one, you are a prototype. I want to keep the interdistances, and that is my new position. So I put the point on the embedded spaces. Or, which is very interesting, why should we map something from a graph into an Euclidean space? Why not consider something more complex? Like, I don't know, constant curvature Riemannian manifold. Why constant curvature and not just a Riemannian manifold? Because a Riemannian manifold, that will be the neural task. But having some constant curvature, these are examples, I like this one, that is hyperbolic constant curvature manifold. We have that the map point for them is very easy to evaluate the distance on these points. Why? Because we have the geodesic function. Those are constant curvature, so we know the distance on those manifolds. I can evaluate this distance between point 1 and point 2. If we do that, again, with the embedding, I start with a training set, some prototypes, and now, for instance, I remap my points not on a Euclidean space, but on a sphere. I don't know if you can see that there. There is a sphere, and clearly once I have a point here, the distance I want to keep to say between this point and this one and this, has to be intended according to the sphere. So it is a geodesic function. But we know that in a closed form, so it is very easy to evaluate the distance between those 2 points. These are some examples of remapping in a different hyperbolic case, Euclidean space, spherical embedding, starting from this manifold. Neural embeddings. So what I'm telling you is that if I have a graph we have methods which allow me to map it into some space. On that space, we can use different distances depending on some prior information I have about that space. We know, for instance, there are some theoretical results that if your graph has a hierarchical structure, so there is knowledge inside and then you extend it, there is still some knowledge inside, like a core knowledge which is built on the top, then the hyperbolic space is the one that you should consider. Neural embedding. I don't know anything about embedding. I want the neural network to identify the proper transformation from the graph space into the embedded space. Let the neural computation define the embedding. Who said that? No. Okay? So the key point now is, how do I represent a graph in a neural embedding if I want to treat it with a neural network, a deep learning neural network? So we need to represent two information, or let's say three types of information. The first one is the adjacency matrix, which is telling me if node 1 is related to node 4. That's it. This one is modeling the topology. Then we have a matrix which is X is associated with the node features. All the features you have associated to nodes. It can be a tensor. It can be much more complex. Edge features. This is a very simple case. Edge features. This is the matrix. If we want, we can have this collapsing into this one. But most of algorithms that you see nowadays in the literature, they try to keep the topology separated from the information to allow the learning algorithm to have some positive inductive bias. So it is better if you know that there is a topology to express that independently and not ask the learning algorithm also to extract the topology information from the attributes. The first algorithm which allows me to do this mapping, this is a totally unsupervised framework, passes through graph autoencoders. In the input, we have a graph, which is represented in the two matrices I told you about. Here we have a graph convolution, like a convolution neural network. Why that? Because in reality, I want to take advantage of the concept of vicinity. That is the real value of a graph. So if I'm here, I'm not interested in what is going to happen here. If I'm here, my neighborhood, my friends is this guy, this guy, this guy. So I want to take advantage of a local information that can be associated with a convolution graph. Convolution done on graphs. So I do all the convolution by looking at the neighbors, at the concept of neighbors. And then you have a pooling in order to deal with the complexity, and then you have the latent space. That is the embedding. Here, having this embedding, once the learning has been perfected, I can do all the chain detection tasks. But I want the embedding to be relevant, so I put a decoder, which is a fully connected dense network, which reconstructs those three matrices. You provide the training set, main graphs, you build the remapping. So what is doing the latent space? It is compressing the information. Still, starting from this latent space, you are able to rebuild the graph. So what you have here is the vector that you need to look at for changes, to detect changes in stationarity. How? Well, you have then IMD, one after the other. You can make the average. You have the central limit theorem. And then you know that distribution is Gaussian. If you know that it is Gaussian, you can set a confidence level. You detect a change or not. Okay? That is one possibility. Very nice. I like this. What I like even more is the possibility to constrain during the learning procedure the distribution of the vector in the latent space. What does that mean? It means that if I put my training set and I want to be able to reconstruct the training set in order to build the mapping, but at the same time, I want to control the distribution of the vectors in the latent space. And I want that distribution to follow a prior distribution. I like, for instance, Gaussian distribution. I put some priors, and I want to impose this distribution to be Gaussian. Can I do that? The answer is yes, by using an adversarial learning autoencoders. The adversarial learning is very, very interesting, and basically what it does is what I told you about. So during this learning procedure, I want to go into details. I want also to impose the output of this embedding to follow a Gaussian distribution, your favorite distribution. Once I know the distribution of this point, I can do anomaly detection, for instance. I can do, which means that I look at the probability that that specific graph is following this distribution. I want something more structural. I build a chain detection test, and I can tell you with some confidence whether there is a structural change or not. How does it work, the adversarial learning on autoencoders? It's very interesting. So just to understand what's going on. It is a min-max game between these networks. We have three networks. Encoder networks, which is the one generating the embedding. The decoder, which from the embedding generates the graph back. And then you have the discriminator. The role of the discriminator is to be able to discriminate vectors coming from the encoder, from here, from vectors coming from the prior distribution. I want to say they come from here, they come from here. What I do here is very strange. So first, repeat until convergence. Think of the learning procedure. You train one step the autoencoder and the decoder, the autoencoder network. You do one learning step on this one. Then you train the discriminator network, which is this one, to be able to discriminate from points coming from the distribution that you set, from those coming from the latent space. You want to say this one is coming from latent space, this one is coming from the known prior distribution. And then you train the encoder, only this one, to maximize the discriminator loss. What does it mean? That now, having said this, I want to change these weights so that the discriminator is confused. It is no more able to say if a data point is coming from here or from here. That's very strange. It can be proved by Goodfellow that this procedure converges. And the outcome, so this is what you do, you see the cross entropy between the different networks with a min-max gain. And the output of that, and now I want to go again into details because I think this is a very strong concept. The output is that you will have now a latent space that is following this distribution. It is mimicking that distribution. Still being able to reconstruct your training data. And then here, you remove all this stuff after training. You have only the coding, and then you look at the data, and you have a statistics, because you know the distribution. So the first step of training, again, you train the autoencoder. Then, you train the discriminator to be able to understand whether this input is coming from the latent space, from the network, or from the prior distribution. And then you want somehow to impose distribution to here. And that's why you needed to confuse the discriminator. And you work on this, you train only this network so that the discriminator is now confused. And why is that confused? Because it is not able to distinguish this distribution from this distribution. That is the idea that is behind this method. Okay? An example. Missed optical character recognition. These are the characters. There is no supervised framework here. It's totally unsupervised. And I wanted to impose a two-dimensional Gaussian distribution. Oops, sorry. Which is this one. So you see the two-dimensional distribution on first feature, second feature. And automatically this procedure cluster all these characters into clusters. That is a side effect, which is very positive. If you look at the distribution, these are new points generated, which are coming from the latent space where I put a new point. These are virgin points, virgin characters, never seen by the network during the regeneration phase. You see 0, and then there is 5, 3, and they smoothly evolve with 8, and so on. So it's very interesting what the adversarial learning is doing. This is the Gaussian distribution. Can I do something more? Yeah, I mean, if I'm able to control the latent space, I can also ask the latent space to follow some Riemannian manifold. I want to have a constant curvature. I want it to be hyperbolic, spherical, not only Euclidean. Can I do that? Sure. This is the basic adversarial autoencoder we saw. Here, I put points that are coming from a given manifold. I also select not only the distribution, but the framework, the manifold, where I'm sampling my points. And that's it. So it goes through the same procedure. In order to improve convergence, because what I'm requesting now is something more complex, that not only requesting the probability density function, I want also the manifold to have a particular structure. So we want to have the learning procedure. That is something that was not proposed by us, but by a good fellow in NIPS 2014, where basically you add a mask. If you look at this bidimensional mask, you see that in a yellow, in a white, which means 1, that is where you would like your points to stay. This is a sphere. And if you get far from this sub-area, because you want a sphere from the shape of the surface, of the sphere, you get a penalization, the yellow, the red, the black. So during the learning procedure, you want your points that needed to follow a given distribution also to stay on your favorite manifold. That is the basic idea. And that is what you do. So basically, there is this is a trick, but the concept, let's look at the concept. You are imposing now the latent space not only to follow a given distribution. You start from here to try to force the manifold, and then you give an help with this membership mask to the learning procedure so that all points will migrate according to the given distribution on that surface of the manifold. You like it to be hyperbolic, you can do that. You can do that. Spherical. Why again constant curvature? Because once I do that, if I have one point here, I can measure the distances. I know the geodesic function, which is a formula. Examples? This is a very simple one. This is a Delaunay oscillation. We have a bidimensional space in this case, where nodes are associated with some positions on a plane. And then we add some noise to the position. So that once you add the noise, the Delaunay oscillation will provide a different graph. We generate the concept of a stationary distribution and not stationary, where the noise has a different distribution. Okay? So this is an example. I'm so sorry that the resolution of picture is not good enough. But these points are also, even though they are different, you see these graphs, they are associated with the stationary case. Here we have a flip of the classes, which means that we have a node which is moving from here to here. And then this is the new distribution. We apply the embedding on a spherical manifold. You don't see that, but here you have this graph goes here. This graph goes to this point. This graph goes here. This goes here. So on the sphere, you can build over time the distribution. But you know the distribution, and you can look at the probability that the new instance is following your distribution or not. These are results where this one is in the red is the baseline, which means that the similarity representation, central limit theorem. And what we have here on the top of that is the adversarial learning, where we impose a Gaussian distribution on a sphere, on a hyperbolic function. On a hyperbolic case. Another application, we have been working with the research center, neurological research center in Toronto, so we have data coming from patients. These are examples of the EEG, interictal stage, pre-ictal stage, the epilepsy is developing, and this is an epileptical stage. This is very clear. If I look at that very well-selected channel, I can understand that something is going on from here to here. But if I look at the matrix of the 64 channels I have on a brain, outside the skull, I'm unable to say this right signal I should look at. It's much more complex. So what we did, we took clips that were given by doctors, related every 0.5 seconds, and we were building dependencies graphs where a node is data coming from one channel, one sensor. We have a framework of a time window of 0.5 seconds, and that is something already done in the literature. You want to reconstruct that information, that signal, with the wavelengths. And you keep the 4, 5 coefficients of that wavelength, the composition, as attributes associated with a node. Between nodes, you have dependencies, which are evaluated up to now according to the Pearson correlation coefficient. You can use a correlation causality, you can use your favorite node. So interictal, no epileptic seizures, ictal. So there is an epilepsy is going on. Again, the same framework, channels, graphs, you see here, we map into the embedding manifolds. You see here now a bit of points. And clearly, this is just an example to show you, if you have this outlier with respect to this distribution, something happens. And that is the chain detection test, which can be sequential, like in KUSU. New data come from the field, I update my state, my probabilistic machine, until I rise an alarm. There is a change in stationarity according to some confidence level. Okay, I'm going towards the end. Some results. These are the data coming from 3 patients. We have the baseline, which is this one, the violet one, which means the similarity representation, very simple embedding, and central limit theorem. I take an average of embedded points, and that is 1 point. It has to follow a Gaussian distribution. Okay? So I can build some likelihood in the embedding space. So if you look at that, the embedding is poor. Still much better than what you see sometimes in the literature. Then we develop the embedding into Euclidean space, which means that we want the autoencoder to transform data into a latent space, which is Euclidean. Spherical, hyperbolic is the orange, mixed. Mixed means that since we don't know which embedded manifold I should consider for my application, I run them in parallel. So one is building the embedding on a Euclidean. Another one is building into a spherical manifold, and another one into a hyperbolic manifold. And then I combine the data in terms of probability terms with a Bonferroni correction to get only one output. And that output is telling me whether there is a change in stationarity or not. So with this mix, which is some sort of ensemble approach, you see that we are, which is the blue one, you see that we are able to detect almost 100% of epileptic seizures in our data. And these are some comments that I made, but let me go to the conclusions. Machine learning based on graph processing is booming. And it is booming because we are considered cyber-physical systems if we are engineers, smart X technologies, social networks. We have graphs. Changes in the graph space are related to those in the embedded space under some reasonable, though strong, assumptions for the manifold and the metric distance we are considering. Those are some preliminary results that tell us at least that, yeah, it does make sense to move into that direction. But people are doing it. Still, there are some results which tell me that if some conditions are satisfied, deterministic or probabilistic, then it does make sense what I'm doing. If I detect a change in the embedded space, there is a change in the graph space. And if there is a change in the graph space, according to some p-value, I will be able to detect that in the embedded space. Adversarial learning and constant curvature manifolds are effective approaches in difficult applications. So I recommend that people to use, if you don't like constant curvature manifold, I can understand that, and I won't get offended, but I think that adversarial learning, imposing the structure of the embedded manifold and the distribution, has many values. So this is my team in Switzerland. So I'm doing this research in Switzerland. And so that's me, an assistant professor. He's a professor in Canada, University of Manitoba, and 2 PhD students. The good news is that we built an open library addressing all what I told you in terms of graph processing. It is on the KIOS framework, which means that it can be used by anyone. It's very, very simple to use that. And there, you can do all the graph processing with adversarial learning, embedding manifold. You can play around and do your research. And that's it. I mean, I hope that I was able to convince you and Professor Politecnico that doing a graph processing is a valuable tool. Maybe that Harris is convinced as well. If it's not, I'm here just to listen to your questions.
Thank you very much. So, thank you, Cesare, for this very exciting talk. Questions? We have time for questions, so please.
Can we use this tools to
You use the.
Okay, close it. No.
But for the others, you go
I should be sorry. I mean, my ears are not.
can we use this analysis to somehow to defend the system from attacks?
Oh, yes.
Those issues?
Yes. So you mean some from malware or cyber attacks? The answer is a yes. Okay, so I was at the conference, Iconic conference, and Professor Sun-Bai Cho from Taiwan and Professor Seisho Zawa from Kobe University, they are working on cybersecurity, and they were using a framework which was previous to this one. In the sense that they weren't aware of the adversarial learning framework. And so they were just one step before that. And because of this spectral library that we just made it available to the public last week. Okay? So they are working now to try to extend their frameworks by imposing distribution. So the answer is yes, and then there are people that are trying to extend what they have done in that frame.
Yes, and the logic is the same. For example, if someone attacks someone else and the distribution of the graph changes too much,
Okay.
so we're doing
Yeah, but I mean, I think that in terms of cybersecurity, you are more interested in, let's say, anomaly detection or transient faults. So the number of instances that you get from the field is limited because you want to stop the cyber attack. I mean, you cannot discover that you go ahead and say, okay, I had a cyber attack, it was too late. I mean, you can even see that. Okay? So in doing that, you needed to play with the statistical framework, not of the learning procedure, which is that, but in order to take advantage of the data you get over time, in order to build the better estimate of the cycle. Okay, but it's less, because if you want to detect change in stationarity, clearly you have a confidence level, but that is a major structural change. Most of the times in cybersecurity, I have been working on the fraud detection for credit cards. Those changes are very subtle. And so you really needed to work on that. But adversarial learning was designed for that purpose. So it is worth it.
Other questions?
Maybe Cesare, actually I was going to ask about the complexity of the discriminator in visual.
Very loud.
So in visual, it's usually when you deal with adversarial that works. The discriminator is usually very hard to design, to do one-shot design. So what about the graphs?
Okay, so I have exactly one picture for you, which was hidden.
Did I ask a good question?
No. So I try also to anticipate the question. So can you see that in there? Not really. Let me move. It is a picture. I mean, it was so nice on my laptop. So very nice. So that is the complexity of what we have. Okay, so the encoder is not very difficult. There's only two layers. This is at the number of linears, 64, 32. Regular calculation functions. That is for the CoE. For the decoder or the autoencoder, 128, 256, 3 levels, 5 to 12. Clearly there is a trial and error in this exercise. But as you can see, those numbers, I'm sure that you like them very much because they are power of 2, because we are using the GPUs nicely provided by NVIDIA. Okay? The discriminator is a fully connected 3 layers. So they are deep layers, but not so crazy, not crazy at all. So you have some convergence, and the probability that your network will converge is rather high. If you're going to use the spectral framework, my PhD student is always available to answer any question that you might have on some particular setting, even though they have been provided in framework. Right?
Other questions?
Yeah, sure.
Can you speak with
I can comment.
It's for everybody to hear me.
Now? Okay. So thanks for the very nice presentation. So what's the largest graphs that you have?
Okay. So up to now, the largest one we considered was the one related to the functional connectivity network for EEG, okay, for epilepsy detection. That was based on 64 channels. Okay? That said, we are now trying to address a problem that has 400 nodes. Okay? I cannot tell you that we will be able to succeed because the computation is a beast there. The problem is, well, is the size. You can imagine the size of the matrices that you input into the autoencoder network. And then you have all the computation associated with that. But we estimate that with 300, we should not have problems. The challenge now is 400 nodes.
Okay, thanks. I have another question about the generation of the graphs. So, how are these done exactly? So, is this time dependent in the sense that if you modify the frequency of the signal, will you get the same graph for the same signal?
No. Okay, sorry. The answer is no, and it depends on the features that you associate to a node. Okay, so let's put it this way. So if for edges, most of the times you try to build dependencies, whether focus, Pearson coefficient, Granger cosine. You want to use one sensor data from one sensor to estimate, to predict the outcome of the other one. And then you have a model. And the coefficients of that model are the attributes you associate with the edge. Okay? So you can, in the terms of dependency, there are many things you do. The change in frequency you are looking at is something which depends on the specific information associated with the time window you look at. In the EEG application, as I said, we want to represent somehow in a compact form that signal in very few coefficients. We use because that is done in the medical community, the wavelet coefficients, able to reconstruct that signal. If you have some priors and your problem is related to frequencies, I do that with some frequencies. With a filter bank, you take coefficients, and that is your representation of the signal. Okay? So what you put in terms of attributes is mostly related to priors that you have about the specific application.
Other questions?
Yeah.
Hi, I have a question regarding noise.
Noise.
Yes. I was wondering, do you have any assumptions on the input data? Have you investigated how noise may affect your singularity measures? And my third question is, can you use the system to remove noise from
Okay, so let me start from the last part. So can I use this system to remove the noise? If I should look at the autoencoder, that is what the autoencoder in a way is doing. Because it is taking the signal, the graph, with its attributes, and it has to reconstruct the graph. Clearly, you don't want to reconstruct the noise. Okay, so that is on the way around. And in terms of what is going to happen if your noise changes, I would rather say that it depends on the specific application, which I know it is not an answer. However, if we have enough data, training set, representing the stationarity condition, conceptually, it means that I'm able to build the conditional probability that you get y given x. And in that way, if there are changes in the noise, so you build your framework, okay? So you know basically everything. So if you have changes in the noise, even though they are small, you should be able to detect them, because that is a change in stationarity. What you get from the field is just the data. But the data is the real data, unknown, generated from the process, plus some noise. And the readout system, the sensor, is not able to distinguish those two. So the answer is yes. But probably you need a lot of data. That is my best estimate.
Other questions? Okay.
All right, thank you very much. Cesare